Okay, hi everyone. I am Alessandra Corsi. I'm faculty at Texas Tech University. I will be timing myself and giving a brief summary of observational results so far from LIGO.
Okay, Alessandra, good to go.
Okay, perfect. So Manuela and all of the organizers of this workshop, first of all, thanks very much for having me. You put together a really terrific agenda, and I'm looking forward to all the talks. My talk here is just a really brief observational perspective on where we stand right now in terms of both confirmed detections or candidate events of the class of compact binary coalescences that contain at least one neutron star using LIGO data. So of course my talk is on behalf of the LIGO scientific collaboration that I want to acknowledge here. So going to my next slide, it was a pleasure to see that there's plenty of young people connected. And so with this overview of the network of ground-based gravitational wave detectors, I guess I want to send a message that the prospects for this field in the future, currently and in the future, are very bright. Here I'm only showing the kilometer scale ground-based detectors, and the image here on the right, nice composite image of the LIGO Livingston and the LIGO Hanford detectors. The Livingston one is the one with the nice green background. They have 4 kilometers long arms, and they are collecting data and analyzing the data together with the twin experiment, VIRGO, which is a 3 kilometer long arm detector in Pisa, Italy. And then last fall, there was a memorandum of understanding signed between LIGO and Kagra, the Japanese also 3 kilometer long arm detector that is currently in commissioning. But the agreement is a very nice future prospect for analyzing jointly data from all these detectors. And I'm not even including detectors under construction or that are planned to have either improvements or brand new detectors in the future, both ground-based or space-based. But so the field is really booming, and the future is very promising, especially for younger students. On my next slide, I want to acknowledge again the LIGO scientific collaboration. There's many institutions across the world, and so this is not just my work. I'm really just honored here to represent the work from all these scientists. Texas Tech is where I am. And of course, to this, we need to add the VIRGO collaboration. And now, as I said, we're also working jointly with Kagra. Okay, so if I had to give my talk in just one slide, here's what it would look. So the summary of the observing runs for the advanced gravitational wave detectors. Observing runs are runs where data of scientific quality are taken, and the first one for LIGO in its advanced configuration started in September 2015 and ended in January 2016. At that time, only LIGO was running. VIRGO did not join this first observing run. This was a very productive run. First observing run in the advanced configuration, and GW150914 was detected. Very first direct detection of gravitational waves. And it also proved, of course, that binary black hole actually emerge and exist. This also was recognized with the Nobel Prize in Physics. And in addition to this, the 01 brought 2 other binary black hole mergers as discoveries. The second observing run was from November 2016 to August 2017. Initially, it was only the 2 LIGO detectors, but VIRGO joined in August 2017, and that was critical. Perfect timing, because as you probably are all aware, in 17 August of 2017, we got the big discovery of the first binary neutron star merger detected directly in gravitational waves. And it was also really the start of multi-messenger astronomy with gravitational waves, as an electromagnetic counterpart spanning really all bands of the electromagnetic spectrum was detected, proving that at least some short flashes of gamma rays that we call GRBs originate from binary neutron star mergers, and plenty of other results, of which I'll give some highlights a bit later. This run also brought 7 more confidentially detected, so highly significant binary black holes, and those are listed in what we call the GWTC1 catalog. So this is great glory, but it's all past glory now. So I'll be giving a bit more details of what's going on, or has been going on more recently, with the third observing run of the LIGO and VIRGO detectors. The run started in April 2019. It was concluded in March 2020, 1 month earlier than originally planned due to the pandemic. In this case, both LIGO and VIRGO, as I said, joined. And the big summary of this is that there are going to be plenty more results coming out, but so far the ones that are public are 2 events that I'll highlight in this talk. The first one, GW190425, is a binary neutron star merger with a total mass larger than anything we know in terms of binary neutron star systems. The other one, GW190814, is a black hole plus a compact object whose mass is very interesting because it falls in what we usually refer to as the mass gap between neutron stars and black hole. This event is also weird in the sense of the mass ratio being Q here being very extreme, at least compared to the binary black hole mergers that were detected during 01 and 02. Another event, because it's a binary black hole, I'm not going to be focusing here, but I'll just mention it, 190412 is worth looking at, as again, it's peculiar in terms of its mass ratio. And I will show later on that more of the results from this run really will be coming out in the following months. In my next slide, I'm just summarizing or trying the hard task to summarize all of the scientific impact that GW170817 brought. And in fact, this slide is probably not making justice to much of the scientific community just in terms of space. But I wanted to highlight a few things about GW170817, as it does remain so far the only binary neutron star merger with such a beautiful link between gravitational waves and electromagnetic counterparts. So in the top panel here, you see the time frequency track of the in spiral as observed in the gravitational wave detectors. And then on the top panel, there is the Fermi light curve. So as you can see, about 1.7 seconds after, this was a detection of an in spiral plus a gamma ray flash or a gamma ray burst. This was also the closest gamma ray burst or short gamma ray burst we had ever detected. And so this detection itself has impact the field in many important ways. The delay of 1.7 seconds between gravitational waves and gamma ray burst is pretty important and encodes a lot of physics. First of all, it allowed to constrain this speed of gravitational waves compared to that of light, saying that they're the same to less than 1 part in 10 to the 15. But also, as I hope to learn more in this workshop, there should be plenty of other physics encoded in that delay, such as the time it takes for a central engine, the compact object that formed after the merger, to launch a jet that then can get power gamma rays, how long the jet takes to break out of the neutron-rich debris, how long it takes to reach the dissipation radius, and so on. So mapping more of these events with coincident gamma ray bursts would be very interesting in the future. Now, what really enabled this the set of amazing discoveries that came with GW170817 is the accurate localization, which I'm showing down here. It was crucial that the event was nearby, again, 40 megaparsec, and that both the LIGO and VIRGO detectors were on. So overall, the final localization was that darker green patch in the sky of 28 square degrees, which seems huge in normal astronomical business, but in reality, it was enough for the worldwide effort that was put to follow this event to discover the kilonova, so the optical transient associated with this event. Here I'm showing just a summary of the red to blue light curves of the kilonova, and we'll hear a lot more in this meeting about it. The key message is there was a slower red evolution compared to a fast blue component, and the properties of the red and blue component of this kilonova told a lot about the formation of heavy elements in those binary neutron star mergers, but also has given very interesting hints about what could be possibly the nature of the remnant left over after the merger, which is something I'm personally very much interested. And so the common idea, the kind of let's call it perhaps more widely accepted idea, is that there wasn't a prompt collapse to a black hole, but perhaps a neutron star survives at least temporarily after the merger and then collapsed. And then I wanted to mention, in addition to this quasi-thermal transient, of course, the jet that powered the gamma rays also gave off an afterglow, but even that afterglow was not as usual. So cosmological GRBs usually show a fast fading glow from radio to X-rays, and the afterglow of GW170817 made us wait patiently for 10 to 15 days to be detected. So you see this raising peak here, curve both in the X-rays and in the radio. And what that told us was, first of all, that the jet we were observing was misaligned, so off-axis, and this was really the first clear off-axis jet discovery in, after more than 20 years of searching. And it also showed us that jet structure is more complex than we perhaps assumed in cosmological GRBs, with a fast core plus wings. The yellow to red curves here, just to highlight that the hunt in radio and X-ray is still going on, with groups trying to catch, perhaps now that the jet has faded below detection levels, trying to catch perhaps a radio glow from the kilonova ejecta itself or the tail of that. Okay, as I said, this is really brief summary. We could talk about GW170817, well, for the entire weekend. In fact, I'm sure we'll hear more. But after this past glories, I want to be giving a bit more details about what has been going on with the latest observing run. And so what you're seeing here is expectations that were published about this run in the so-called LSC observing scenario papers, the LIGO review. And for LIGO and VIRGO here, you see the projected distance ranges for detections of binary neutron stars, assuming a single detector's signal to noise ratio of 8. And so the ranges expected for LIGO are between 110 and 130, 50 for VIRGO. The detection rates, of course, due to the uncertainties, are a bit scattered. So it's anything in between 0 and 10 for binary neutron star detections, and even more uncertain, of course, for neutron star black holes. And then expected localization areas, which are critical for electromagnetic transient identification, are in the range of hundreds of square degrees. And this assumes that there is a detection with a combined signal to noise ratio in the network of 12. So now, how do these compare with what actually happened? Well, first of all, the timeline, you're gonna hear about O3A and O3B. So I just wanted to clarify, the O3 run has been split in two parts. The first part, which is usually referred to as O3A, run from April to September of 2019. Then there was a commissioning break of 1 month. And then the second part between November and March, it was, as I said, interrupted because of the pandemic. Now you see here a question mark because there was a discussion whether the O3 run will start again or not. And that is not going to happen. So now we're looking into, detectors being improved for O4. If you look at the actual ranges that were reached for binary neutron star and spirals, here are two plots. Top is for the first part of O3, and bottom plot is for the second part of O3. On the x-axis is the angle averaged range in megaparsec, and then on the y-axis is the total time spent at that sensitive distance. And the LIGO Hamford is in red, Livingstone in blue. You can see it's pretty much in the ballpark of what was expected. The major difference is nice to see between O3A and O3B in terms of improvement for VIRGO, which is here in purple in terms of distance reach. So basically the distance horizon goals were reached. It's not just important that the detectors are up and running. Of course, it's critical to have simultaneously the free detectors taking good data, because free detectors are, well, crucial for sensitivity, of course, but also for sky localization. So overall, the statistics, some of you might be interested in, because that impacts, expectations for events rates and so on. We're a bit more than 50% triple coincidence time, free B, a bit more than 85% with 2 or 3 detectors, and then there were downtimes. Overall, none of the detectors were on for almost 3.5% of the time, but this was pretty good statistics. As you may know, the big thing that changed with the third observing run is also that the LIGO and VIRGO detectors started issuing public alerts. And so for the younger people that are logged in today, you can go to this link, and this is a nice link because you can find, first of all, the alerts that were issued, but it's also a guide of how to interpret and read the information given in this alerts. So on the right plot, you can see a cumulative count of events coming from first observing run, second one, and the 2 parts of the third observing run. In the end, this program of public alerts changed the situation. As in previous runs, the alerts would only reach partners that have established memorandum of understanding. The goal of the O3 run was to really open this to the astronomical community so that prompt follow-up could be enabled in a much more efficient way. And so overall, if you look at this plot, the number of alerts that were sent out during O3 and not retracted were a total of 56. Now, of course, these alerts have, in general, a lower false alarm threshold than the secure identifications of events that we publish after offline analysis. So you have to, take them with a grain of salt, and that's why this guide is useful. In the alerts, you find an initial classification of the compact binary coalescence event, and this graph here on the left is useful to understand a bit what they mean. So if it's compact binary coalescence with 2 objects whose masses both below 3 solar masses, then we call that a binary neutron star merger. Something with a mass greater than 5 solar masses is called a black hole. So you could either have binary black holes or neutron stars black holes if one of the objects is 5 solar masses or more. And then in between, if there's an object in between this mass range, then those are the type of events that are called mass gap in the initial real-time classification. Here is just a timeline of how the online analysis and the alert system worked. There typically was an automated circular going out within the first minute or so. Then there was a rapid response team, which was called to make sure that some data quality criteria were looking all right, and making sure that the event didn't need to be retracted or things like that. So that happened typically within the first hour. And then more usually other GCNs follow in longer time scales, either updating the classification or if there's any need to update the sky map. And again, all this information can be found at this website. For this specific talk, I just wanted to give you an idea of what the alert system looked like. So overall, this is a summary of all of the preliminary alerts that were sent out. The classification you see here is the preliminary classification, so the online one. And I am highlighting the two events that I mentioned before, which are the only two ones so far in this category, either binary neutron star, black hole neutron star, or mass gap event that so far were published by LIGO in separate papers. And so the false alarm rate, of course, is again the one estimated via the online analysis, and it gets refined offline. But what you can see is that those two events in particular had a low false alarm rate to start with. By the way, when you see something this high, all it means is that this is obviously an extrapolation, that there were no background events comparable to the one observed, and then the refined offline estimate of the background quantifies or sets an upper limit on that false alarm rate, which is more realistic. So let me talk a little bit more then about these two events, but the message here is stay tuned for the overall catalogs that will come out as publications from the LSC and VIRGO. So they will say the final words about what this alerts actually ended up being. So the first event that I've mentioned a little bit before is 1904-25, and a lot more about this will be, I expect, will be said in later talks, especially Richard O'Shaughnessy's one. So I'll just mention a few things. First key thing, the sky area was rather big for this event, 90% more than 10,000 square degrees. And the reason is Hanford was off at the time. It had a signal to noise ratio that stood off pretty much the background distribution. So what you can see on the right-hand side is the background in terms of SNR and a combination of SNR and what you can think about as chi-square for all of the background in the detectors. This is the shaded area. And then the star is showing you the significance of 1904-25 compared also to GW 1708-17 in LIGO, Livingston, and Hanford. So although it was not as strong as an event, it clearly stood out of the background distribution, but there is no electromagnetic counterpart for this. Again, the main challenge is the huge sky area, in addition to also a larger distance. However, it's very interesting, and again, you'll hear more about this because if you consider the total mass of the event, the orange and blue distributions here show the constraints from the gravitational wave signal with different prior assumptions on the spin. But regardless, you can see it's pretty much far off from the distribution of galactic binary neutron star mergers in terms of total mass. The main line you want to compare it with is this dashed line here. So this says something about perhaps a formation channel that is different in terms of evolution of the binary neutron star merger. Of course, we cannot exclude that one or both the objects are black holes, but this again would require formation channels that are quite not standard, I would say. And then the discovery of this event also updates a bit the rate for BNS mergers, specifically the lower rate compared to what was established by GW 1708-17. The other notable event is the one, as I said, which has a black hole plus a compact object whose mass falls in the gap. So it's about 2.59 solar masses. And in this diagram, it shows you again the constraint of M1 and M2 coming from the gravitational wave emission. And again, I won't go into the details, but as you can see, what's going on is it's a pretty extreme mass ratio object with the smaller one in the gap and the larger one about 10 times more massive. And so here the question again is, is this a new type of astrophysical event? It's not clear whether M2 is a black hole or a neutron star. It is comparable to masses of the Abyss millisecond pulsar or the black hole candidate remnant from GW 1708-17, but the question here remains open and so interesting to explore. And so this is my summary slide. In the end, we are populating the masses in the stellar graveyard more and more. The three big, events here in the show, GW170817, and these other two from O3 that I showed are pretty puzzling in terms of all having some link to MGAP objects. But again, we expect to populate this diagram more. And here goes my alarm. So stay tuned for further results. And I'll just like to thank you for your attention and hear and take any questions.